Now that we understand what petroleum data analysis means and where the data come from, we move into the next major part of the lecture: conventional methods. In this section, we will see how petroleum engineers traditionally analyze data from exploration, drilling, development, and production. This slide introduces exploration data and also notes that we do not discuss exploration analysis in full detail in this course. Still, it is useful to understand its role. Exploration data analysis is one of the earliest stages of petroleum decision-making. Before we drill an expensive well, we need to know where the reservoir may be, what structures exist, and whether there are signs of hydrocarbon accumulation. This is a high-stakes stage. A poor interpretation here can lead to a dry well, which means huge financial loss. So even though we are not spending much time on exploration analytics today, we should respect how important it is. This slide highlights the use of commercial software, such as Petroleum, to analyze seismic data. The slide also asks, which key information can we obtain from seismic data? The answer includes interpreting faults in channels, recognizing depositional environments, understanding structural deformation history, identifying prospective hydrocarbon zones, and selecting locations for drilling. This is exciting because seismic interpretation is like trying to read the hidden architecture of the Earth. It is a bit like a doctor using medical imaging. The doctor cannot directly see inside the body without surgery, so they use imaging tools. Similarly, geoscientists cannot directly see the deep subsurface, so they use seismic reflections to infer what is underground. When you look at seismic data, you are not looking at a direct photograph of the reservoir. You are looking at a physics-based response that must be interpreted carefully. Faults, channels, folds, traps, these are not always obvious. That is why software helps, but human expertise is still crucial. Now we move to drilling-related data. Drilling is where the project moves from indirect interpretation to direct contact with the subsurface. This is a major transition in petroleum engineering. Once a well is drilled, we start getting real physical evidence from the formation. Drilling data can include rate of penetration, mud weight, drilling torque, cuttings description, gas shows, formation pressure, and other operational indicators. These are not just operational numbers. They also tell us about formation behavior, safety conditions, and reservoir characteristics. So drilling data analysis is not only about efficiency, it is also about reducing risk and learning about the reservoir. This slide shows that commercial software is also used to analyze drilling and well logging data. From these analyses, engineers can estimate permeability, porosity, shale volume, water saturation, gas saturation, and distinguish oil zones, water zones, and gas zones. This is one of the most important areas of petroleum data analysis because well logs provide continuous information along the wellbore. Think about how powerful that is. Instead of having only a few core samples, we get a nearly continuous record with depth. A nice way to explain this to students is, if seismic gives us a regional picture and core gives us highly detailed local truth, then well logs sit in between. They are continuous along the well and extremely valuable for connecting geology with engineering. This is why log interpretation is one of the foundational skills in petroleum engineering. This slide highlights core data and details of target zones. Core data are extremely valuable because they provide direct physical samples of the reservoir rock. Unlike seismic and logs, which are interpreted measurements, core lets us hold the rock, analyze it in the laboratory, measure porosity, permeability, capillary pressure, wettability, and much more. Students should appreciate how rare and valuable core data are. Cores are expensive to obtain, but they often serve as the ground truth for validating other interpretations. If logs suggest high porosity, core can confirm it. If reservoir simulation needs relative permeability trends, laboratory core analysis may help provide them. So core data are like the most trusted witness in a technical investigation. Now we move to well test data. Well testing is another major part of petroleum data analysis because it tells us about productivity and flow behavior. While logs and core tell us about rock properties, well tests tell us how the reservoir behaves dynamically around the well. Well testing is very powerful because it connects geology with flow. A reservoir may look good on logs, but if well test performance is poor, then the economic value may be less than expected. So well test data bring reality into the discussion. This slide explains the multiple purposes of well testing: confirming discovery and productivity, cleaning up the well, obtaining rate measurements, taking large volume fluid samples, understanding well and reservoir performance, investigating flow behavior around the wellbore, and supporting field development strategy. It also emphasizes preventing huge financial losses. This is a great example of why petroleum data analysis matters. A well test is not just another operational procedure. It is a decision-making tool. From the test, we can learn whether the well is productive, whether damage exists near the wellbore, whether the connected reservoir volume is large or small, and whether the field is worth further development. So in simple terms, a well test helps answer one of the most expensive questions in petroleum engineering: is this discovery commercially meaningful or not? We now move from drilling and appraisal to development data. Once a field is considered viable, petroleum engineers need to plan how to develop it efficiently. This requires a large amount of integrated data. At this stage, petroleum data analysis becomes more complex because we are no longer asking only, is there hydrocarbons here? Instead, we are asking, how should we develop the field? How many wells do we need? Where should they be placed? What recovery strategy is best? What risks are involved? This slide lists materials used in field development planning, including reservoir top and base surfaces, wellheader information, SAL porosity and permeability, unique well seed values, and software such as Petroleum. This is a good moment to remind students that development planning is a data integration problem. No single dataset is enough. Structure maps define geometry. Well data define local rock properties. SAL data define flow-related properties. Fluid data define PVT behavior. Operational constraints define what is feasible. The field development plan is therefore an engineering synthesis of many different data sources. This slide shows porosity model, permeability model, water saturation, and static model concepts. The slide also notes that if average water saturation is 0.37, then hydrocarbon saturation may be estimated as 0.63. This is a great place to make the lecture interesting. You can tell students that a static model is like building the hidden body of the reservoir. We define where the reservoir exists, how good the rock is, and how fluids are distributed initially. Porosity tells us how much pore space exists. Permeability tells us how easily fluids move. Water saturation tells us how much of that pore space is already occupied by water. When we combine these together, we begin to estimate storage capacity and hydrocarbon potential. So static modeling is not only about visualization. It is about building the physical basis for development decisions. This slide introduces the dynamic simulation model, with an initial model and natural depletion scenario. This is where petroleum data analysis evolves from static description to dynamic forecasting. In other words, the static model tells us what the reservoir is, while the dynamic model tells us what the reservoir may do over time. This transition is very important in engineering. Once we have a simulation model, we can test natural depletion, water injection, gas injection, and various well controls. So petroleum data analysis at this stage becomes predictive, not just descriptive. Now we enter the production phase. This is where data analysis becomes continuous and highly practical. Once wells are producing and facilities are installed, engineers monitor field performance closely. Production data analysis tells us whether the field is performing as expected, whether problems are emerging, and how future performance may evolve. This is where time series thinking becomes especially important. The reservoir is changing all the time. Pressure drops, water cut rises, gas production may increase, and well deliverability may decline. So production data are not static. They are living data. This slide explains that production can begin as soon as wells are completed and facilities are installed. Performance is evaluated using field data, and these data are used to forecast reservoir performance. It also notes that decline curve analysis is a popular approach. This is an important engineering idea. Once a field starts producing, the field itself becomes a source of feedback. The reservoir is now telling us whether our original expectations were correct. If actual production differs from forecast, engineers must ask why. Was permeability lower than expected? Is water encroachment stronger than expected? Is there completion damage? Is pressure support weaker than expected? So production data analysis is like listening to the reservoir after the field begins to speak through rates and pressures. This slide introduces decline curve analysis, or DCA, as an empirical technique for predicting oil or gas production by fitting rate versus time. It also notes that some reservoirs may sustain nearly constant production for some period, but in general, rate declines over time. DCA is one of the most practical tools in petroleum engineering because it is simple, intuitive, and often very useful. The key idea is that production history contains patterns. If we can identify the decline trend properly, we can forecast future production. This slide shows that an exponential equation can be fitted to historical production data to predict future production. It also includes exercise 12.1 about an oil well declining from 4,800 stb/day to 3,700 stb/day over 2 years, asking for the decline factor and the time to reach 100 stb/day. This is a perfect teaching opportunity because it turns theory into calculation. When students solve this exercise, they realize that production forecasting is not abstract. It directly affects reserves estimates, economic planning, facility sizing, and development strategy. If a company overestimates future production, it may overbuild infrastructure or make poor investment decisions. If it underestimates production, it may miss value. So even a simple decline equation can have major financial consequences. This slide shows that an exponential equation can be fitted to historical production data to predict future production. It also includes exercise 12.1 about an oil well declining from 4,800 stb/day to 3,700 stb/day over 2 years, asking for the decline factor and the time to reach 100 stb/day. Can you answer? Here I can help you through the solution step by step. Start from the exponential decline form, substitute the known initial and final rates, solve for the decline constant, and then use that value to estimate when the rate reaches 100 stb/day. What is important pedagogically is not only the final answer, but the interpretation. The decline factor tells us how quickly the well is losing productivity. The predicted time to 100 stb/day gives a sense of remaining productive life under the same decline trend. That is why production analysis is so closely tied to economics.